So, the scientific method. A scientist makes observations about the world and then thinks of an explanation, a model that explains what is going on and compares the two in a validation process. But now what if there are two scientists who of course have two models that are not exactly the same? Are they going to fight? Well, if the models were made for the purpose of understanding the world, then at first sight there is no real reason to suspect a problem, is there? I mean, supposing both models accurately predict the observations that we are interested in, we can just use either one. And if one is more accurate than another, well, we use the one that is more accurate. Now, if one is more accurate in one situation and the other is more accurate in a different situation, or for one purpose or a different purpose, then we use the one that is more suitable in each situation. So why would they fight? But from a physicist point of view of understanding the world, it is of course very unsatisfactory if you need two models in two different situations, especially if you need the models to tell you in which situation you are. At the moment, there is still a big debate because large-scale phenomena are better described using relativistic mechanics, while small-scale phenomena are better described using quantum mechanics. And there is not a single model. Well, there are some attempts, but there's nothing yet that is completely satisfactory that actually combines the two. So physicists do not feel that they really understand the entire world. They understand parts of it, but there are mysteries as well. Now, for engineers, the problem of having two different models of the same system and the problem of making sure that these models are somehow comparable is even bigger. Because engineers have to cooperate together to build a system. Seldomly you can actually do it completely on your own. And if then two engineers have a different model in mind, how will they ever know that they're going to build the same system using it? Especially because since the system has not been built yet, you cannot compare the two models based on experiments. Physicists run into a similar thing, of course, because if they propose an experiment, it has to be an experiment that is applicable to both models. Otherwise, you already have an experiment that contradicts something there. But it is not in the understanding, at least not in the understanding of the world, that the problem lies, but in the understanding of each other. The two scientists who have two different models have to somehow find out what the other scientist means. So what follows is a discussion between the scientists in which they ask the question, what do you mean, a lot? And that is a lot like the scientific method, the scientific process, in that every question that you ask to the other person is a kind of experiment, a thought experiment, to figure out whether what you think they mean is also what, well, comes out of them if you ask them. And it is really much like the scientific method in the sense that even if you've asked 1,000 questions to the other person, you can never be sure that you completely understand them. Only when you hear them say something like, well, I never said that, or no, that's not what I mean, then you know that you misunderstood. So you can only tell that your ideas about their model are wrong. You can never be completely sure that they are right. In that sense, the model, the mental model that you are making of a model of somebody else is again really a model. In linguistics, a distinction is made between syntax, which is whatever you can say, words or other language constructs, and semantics, which is what you mean by them. In that same way, computer scientists make a distinction between a syntactic model, which is something that you can write down, and a semantic model, which is usually some kind of abstract mathematical object. Syntactic models can be pictures, can be drawings of components, graphs, subsystems connected together, drawings of electrical circuits, but also formulas and equations. The syntax of these is always finite because, well, you have only a finite time to say it or a finite amount of space to write something down or to draw something. Whatever you mean by them can be infinite in nature. When I write down this symbol, that's just a symbol. But its semantics is that there has been a count of 7 objects. When I write down this symbol, that again is just a symbol. But many people associate it with a value that is known to be represented by an infinite number, well, an infinite amount of numbers, an infinite series of numbers. When I write down x plus y, these are just symbols again. Many people will associate these symbols as x is a placeholder for a number, y is a placeholder for a number, a variable, and the plus indicates that they have to be added. But there are also computer scientists who think that x and y represent processes, and the plus represents a choice between these processes. They give semantics to these expressions by defining what a process is exactly as a mathematical structure. For example, they use label transition systems for this. And there are many other ways in which the meaning of x plus y can be defined. When electrical engineers write down an electronic circuit, there are standard ways to transform this circuit into a set of equations using Kirchhoff's laws. These equations are just a representation of the same thing, but they use a different kind of syntax. The mathematical semantics of these equations are usually taken to be functions over time of values that represent the currents and voltages in the real system. The mathematical semantics of the circuits drawn are actually the same thing. So the mathematical semantics gives a basis for comparing the two completely different forms of syntax. The process of giving semantics to a syntactic model is called formalization. It ties the symbol to the notion, the symbol 7, to the notion of an abstract set with 7 elements. It ties the set of equations to the set of solutions, the set of functions over time. Whenever two models need to be used together, it is useful to formalize them into the same semantic model. By doing so in a structured way, we can build an additional opportunity to discover discrepancies in our understanding of the world. Because we can now ask critical questions, we can do thought experiments on our models without performing actual experiments in the real world. These are just experiments that make us understand our models better, of course. They do not make the understanding of the real world better. For that, you need the actual connection to the real world. Of course, we are cheating a little bit here when I say, oh, it's a set of 7 elements, an abstract set of 7 elements, because those words are just syntax again. But we've all shared a mathematical training that makes that I can be pretty sure that when I say an abstract set of 7 elements, that you have the same ideas of what that means, or at least that you will agree on the things that we can do with this set, and that those things are actually the same as what I have in mind. So by using formal mathematics, we allow ourselves to ensure that we have the same understanding of a model, and to ensure that if we have different models, that these models are actually models of the same thing. Now back to the topic of this module, performance analysis. That is a situation in which it is actually custom to have multiple models, even if you're working in it alone. You might think that, well, measurements are enough if you want to know the performance of a certain system, right? If you want to know how fast the car goes, you press the pedal and you go. But that would give you an idea of, indeed, the performance metric of the speed of the car, but it would not really give you an understanding of how that performance is obtained. For that, you need either a simulation model or an analysis model. And coupling these models to the measurements that you made gives you a certain understanding and a certain confidence that you understand how the car achieved the performance it got. If you are designing for performance, then you don't have an actual system to make measurements on, then you might actually want to have a simulation model as well as an analysis model and compare them with one another. By comparing the analysis to the outcome of simulations, you get more confidence that your analysis model makes sense. And by comparing your simulations against an analysis model, you might get more confidence that you did not make a mistake in describing your simulation model. So, in a good performance study, you at least have 2 out of 3: measurements, simulation, and analysis. As a common semantics for the models that you use in performance analysis, we often take the set of executions of the system. By describing how the system may go through different stages and describing that in a mathematical way as a series or as a labeled transition system, you precisely capture what the system can do. And you can do that for a simulation model as well as for an analysis model. And you can also easily map whatever you have as a mathematical semantics to the actual outcome of experiments. So the set of executions is a very nice common way of looking at performance analysis models. And in this module, you will hear me talk about executions quite a bit. In summary, whenever you encounter a new model of a system, you want to look at both the syntax and the semantics. And preferably, you want to find a semantics for that model that matches the semantics of other models that you already know, so that you can make a valid comparison. If it's not possible to make it match exactly, you at least want a mathematical relationship between the different semantic models. And also, if you're reporting on your own modeling work, you want to give your audience the opportunity to ask questions about the model that you've made. So it is nice if you have a section on syntax so that they exactly know how you are going to describe your model, and that you have a section on the semantics so that they can test their ideas of what you mean by your descriptions with their own mental models of what they expect. Having that distinction is actually very common in theoretical computer science, but if you're outside that field, you may have to search for it a bit. But my experience is that it really helps to dig up the difference and the distinction between the syntactical model that they are using and the semantical meaning of it. Also, if you're writing a report on a performance evaluation, it helps the reader if you make a distinction between the measurements that you did, if you give them a separate section, and the simulations that you performed, and maybe the analysis that you performed. And then, of course, there is a concluding section in which you compare the outcome of the 3 or 2 of the 3, so that you can actually convince the reader that everything is in order, that they all agree. If they don't agree, well, that's what the next video is going to be about, finding out what errors are made and where they came from.